This is the third day of notes for Chapter 15 on energy and chemical reactions. It's a short one because we're just doing the last section. This talks about reaction spontaneity, so we'll get started with it. So spontaneous, as far as reactions goes, this means that a reaction, once it's started, will proceed on its own without any extra intervention or outside energy or help. Doesn't mean that it's just going to go on its own. Some reactions will occur at certain temperatures and just happen, but generally you have to have something we call activation energy in order to get this going. Like lighting a fire. You light the fire, you have to add the energy to get it going. That's the activation energy. Once you've activated it, you could walk away and it keeps going on its own because the fire creates enough energy to create more fire, and it keeps going until all the fuel's burned. So spontaneous means that once it's started, it continues on its own without any outside intervention. The opposite would be non-spontaneous. Two factors determine spontaneity, and this will be on the test and the quiz. The two factors are entropy and enthalpy. You already know enthalpy, that's the heat energy or the heat content in a system. Entropy, the book defines it a little differently, but probably the best definition of that would be a measure of disorder. So the more disordered things are, the more entropy. And one of the laws of thermodynamics, second law of thermodynamics, tells you that the more are in the universe, we continually are going towards more entropy. In other words, things drop and break and they fall into more pieces. Plants grow because they have energy, which is less entropy, but then eventually they don't have energy anymore when they die and they fall apart and break into lots of little pieces. More little pieces is less ordered. Plants are real ordered. It takes energy in order to do that, but once eventually they all die and then they fall apart and become more disordered. So we'll move on. There are 6 ways you can predict the entropy of a system, and the book has 5 of these, but there are probably pretty good 6 ways. First of all, entropy increases going from solid, liquid, gas, plasma. So a solid is nice and neat, organized. When it melts, it creates a little bit more of a mess. When it turns into a gas, now it's all over the place. And in plasma is even just a higher energy of that higher temperature. Second, dissolving of a gas in a solution decreases entropy. So we have ordered something a little more. We've taken it from all over the place to in a solution. So we've organized it a little bit. The more gaseous substances indicate an increase in entropy. And that's kind of related to the last one, because instead of having gases all over, we've organized it. Well, if we put more gases all over, then we've got higher entropy. So the more gases there are in a product or reactant, the more entropy. Entropy increases when a solid or liquid dissolves in a solvent. So this is different from gas. Gas, we're taking a disorganized thing and putting it into solution. But when we have an organized solid, little crystals are nice and neat, and we dissolve that, or a liquid, that causes it to be more spread out and more entropy. Entropy increases with temperature, so the higher the Kelvin temperature, the more entropy. More parts indicate a higher entropy. You've got a vase or a vase, and you drop it, and it's going to be in little pieces all over. That's more entropy. If you start with H2O and you break it into H2 and O2, that's more parts, more entropy. So Gibbs free energy, named after a scientist, that's why it's capital G. We generally call this free energy. Free energy, Gibbs free energy, same thing. And it is the energy that's available to do work. So like in our car burns gasoline, gasoline produces energy, and it's excess energy that the reaction doesn't have to have. That excess energy we could harness and make it turn the engine and do work, drive us here to school. The main equation for calculating free energy is delta G equals delta H minus T times delta S. This is a good equation to remember. I do give it to you in the possibly useful, but it not only solves problems, it also answers the question for us: what are the factors that cause free energy, and how do those factors work? Because the two factors are enthalpy, delta H, and entropy, delta S. So what you need to think here is, all right, a negative delta G is a spontaneous reaction. Positive delta G is non-spontaneous. What kind of H, if we didn't look at the S at all, what kind of H will give us a negative delta G? Well, if you know the only thing there is delta H, it has to be a negative delta H to give a negative delta G. So in other words, a decrease in heat energy is favorable to making reactions go. Likewise, if we just make the Kelvin temperature 1 and that's identity and it goes away, and let's say that the enthalpy was 0, then all we have is delta S. What kind of delta S makes a negative delta H? Well, look in front of it, you'll notice there's a minus symbol. So a positive delta S, which is an increase in entropy, becomes negative because of the minus in front of it. A positive delta S is what's good to drive a reaction. So that tells you the both items that are involved in making a reaction spontaneous, because remember, negative delta G is a spontaneous reaction. That's something important to remember. And this is on your possibly useful page. You just go look at it when I ask you what are the two factors that cause spontaneity. And they're right there in that equation. So here's an example problem. The example is we have temperature of 25 degrees. And remember, add 273. Just like the chapter with gases, we have to have Kelvin in order to do this equation. So add 273, you get 298. Our delta S is 322 joules per Kelvin. Remember, that's joules. The other factor is kilojoules. We have to bump the decimal over 3 places smaller, big unit, smaller number, in order to get 0.322 kilojoules per Kelvin so that we can use it with our other factor. And the delta H is 145 kilojoules. Plug that into the equation, and the question answers what is the Gibbs free energy and is this reaction spontaneous? And when we go on to the next slide, you see the solution there. And we end up with a positive 49 kilojoules. That means not spontaneous because it is positive. It has to be a negative to be spontaneous. So pretty quick. There's not a whole lot more on this one. That finishes up the chapter. And you know, if there's anything else you need to pick up some more time on, go out to the website or pick up some of the extra practice problems in class, work on your review and do those problems. Good luck.